All right, guys, what we're going to be looking at here in this section is what are known as improper integrals. This idea at first seems like it's kind of, you're going to be like, okay, that's not that big of a deal. I think I understand exactly what's going on. But this is one of the more difficult ideas, honestly, to wrap your head around what's happening in these problems. That doesn't mean that what you do is overly difficult, although in this video we'll talk about some things that in order to earn all of the points on the AP exam, you need to do certain things when you see an improper integral. Realize that what you do is not that hard, but the idea behind what we're talking about is. So to get started, let's take a look at this integral. Okay, I've got the function 1 over x squared. And if you were to look at 1 over x squared, it looks like this. If I look at the function, it looks like this, and it looks like this, and it never, ever, ever touches the x-axis. So if I were to ask you what is the integral from 1 to infinity of this particular function, remember the integral is telling us what is the area that exists between that graph and the x-axis. And looking at this, you'd say, well, I mean, this is what most people say anyway. They say, well, there is always more area that is being added because there's a horizontal asymptote here at x equals 0. So this graph never reaches the x-axis, which means there's always more and more and more and more and more area that's being added. So most people would say something like, oh, that's going to be infinity, or that does not exist because there's always more area that is being added up. And although I understand why most people think that, that is not what this area actually is. These are what are known as improper integrals, and we'll come back to that in just a second. Now, what we do, first of all, and this is very important for the AP exam, to use proper notation. A lot of people lose points when they're looking at these problems because they know what they're doing, but they don't write it down correctly. So when I look at this function, anytime I have a constant number to infinity, or vice versa, where the infinity is on the bottom, negative infinity, either way, what we have to do is we have to create an improper integral where we say, okay, I'm going to change this infinity to be the limit as b approaches infinity, and I put a b up there. And most people, when they see that at first, they're like, okay, I don't understand. Those mean pretty much exactly the same thing. The best way I know how to describe what's going on here without getting into too much technical detail is, although we will be doing the same thing during the entire problem, we'll evaluate it basically the same way. In order for us to use the fundamental theorem of calculus, I have to have a constant number on both the top and the bottom of my integral. And if I have infinity up here, infinity is not a number, it's just an idea, if you will. When I say the limit as b is approaching infinity, although it seems stupid and you're like, okay, well, that you're saying the same thing either way. Now I'm saying I'm approaching a number that is just very, 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 very large. So let me show you kind of how that, before we get to that as well, here's another two terms that we need to deal with that will come up often in the rest of this class. So we'll need to talk about both of these often. The two words that we're going to be talking about are converges, or sometimes you see the word convergent, and diverges or divergent. When an integral converges, one of these improper integrals, what that means is the area is actually equal to a specific number. So like when we were looking at that 1 to infinity of 1 over x squared dx, I told you that that's equal to something. That means that we would say that that particular series is convergent, or it converges to a specific number, and we'll look at how to find that in just a second. When we say that a series diverges, basically what we're saying is when I have one of these, and we'll figure out how to determine whether or not it's convergent or divergent shortly, but basically what it means is if I try to evaluate the integral and what I get is either infinity or negative infinity, that means that there was no way to actually stop counting the area. And again, there is a way that we can tell what it's going to be. We just have to look into this a little bit more to figure out what the answer is. So let's take a look at this one. Now, what we're going to do, because I want to know whether this converges or diverges, and if it does converge, I want to know what it converges on. So the way that we show that is the very first thing we do every single time is we change these problems to limit problems. So I say this is going to be the limit as b approaches infinity of the integral from 1 to b of 1 over x dx. Now there's some minutiae here that's important for the AP test that's not necessarily important for you to understand what's going on in the problem, but I don't want you guys losing points just because you're writing these things out wrong. So if I have an integral, and now I'm going from one constant number to another constant number, hopefully the very first thing that you can see is that I can use the fundamental theorem of calculus. So I can take the ln of the absolute value of x Take the antiderivative of that, then I plug in the top and I plug in the bottom. So I get the ln of b minus the ln of 1. The ln of 1 we know is 0. Now this is where you got to be careful as well on the AP exam. The limit as b approaches infinity, normally what we do with the limit is we take the limit and we plug it in. However, in this case, I cannot just plug infinity in because infinity is not a number. So although you could do that and you could say, okay, what is the ln of infinity? And we would realize that the ln function just gets bigger and bigger and bigger. So that would be infinity as well. I cannot put infinity in right there. Instead, I would say this entire limit is either equal to infinity or it does not exist. Now, what that means is, in this case, because this is not a specific number, you're probably asking yourself, will that always not be a specific number? But because that is not a specific number, we are going to say that this particular series diverges, okay? So it's a divergent series. Hopefully that kind of makes sense. Let's go back. I told you guys earlier that this one was going to be convergent. So I do the same thing that I did before. I do the limit as b approaches infinity of the integral from 1 to b of 1 over x squared dx. I'm going to carry it out. Okay, I'm going to move the x squared up to the top, make it x to the negative 2. So I'm going to, the antiderivative of that is x to the negative 1 over negative 1. Or, because I'm going to have to evaluate this, I'm going to go negative 1 over x evaluated from 1 to b, and this is the limit as b approaches infinity. So I take the b and I plug it in, so I go negative 1 over b minus negative 1 over 1, because I plug in the 1 as well. Now, this is the limit as b approaches infinity. If I take infinity and I put that in for b right here, I'm going to get negative 1 divided by a massively huge number, which for all intents and purposes is 0. So what I get here is 0 plus 1, which is just 1. That is what this improper integral is equal to, so we can say that this particular integral is convergent. Now, it's kind of hard to wrap your head around when you look at these things, because I said 1 over x squared, if I were to look at that graph, it looks like this, whereas 1 over x looks very, very similar. It still has that asymptote. It still is, as we go to infinity, the y value is getting closer and closer to 0. The problem is, and we'll discuss this more when we talk about a different idea, but the problem is it's just not getting to infinity or to 0 fast enough. So there's always a little bit more area that I can count up, and we will talk about that at another time. Don't worry about it too much right now. Just hopefully your mind's like, what in the world is he talking about? Now, the nice thing is, if we look at a function that we'd like, the type of functions that we've been looking at, like 1 over x to any power, the nice thing, and it has to be written like this, but the nice thing about those functions is I can tell immediately whether it's going to be convergent or divergent without having to carry the entire thing out. The integral will always converge if this number power is bigger than 1, whether it's 3/2 or 20 or 30. Whatever the number is, if it's bigger than 1, it's going to converge. If that number is less than or equal to 1, then it's going to diverge. So if I look at one of these immediately, you're like, okay, I can tell whether or not that's convergent or divergent just by looking at it. Now, and we've already talked about, I'm actually going to skip the talk about vertical asymptotes for right now, just because usually, well, we can talk about it real fast. If I were to look at 1 over x squared as x gets closer and closer to 0, we're going to run into the exact same problem that we did when we had an integral that was headed towards infinity, and that is there's going to be more and more and more area that exists up here. So what we have to do on these problems, one like this, is we look at this and we notice it's of the same form. Notice I've got 1 over x to the 1/2 power. If I know that I have an asymptote, and that's the key to these problems, that's why I was going to skip them for a second there, because if I have one of these problems, I have to know what the graph looks like in order to understand what is being asked of me to find. So what I want is the area from 0 to 1 here. As I get closer and closer to that asymptote, we have to ask ourselves, am I going to be able to count that area or am I not? And again, I don't want to get into it too much, but basically, if I get really close to a vertical asymptote, the rule that we used before flip-flops. If that number is less than 1, less than or equal to 1, then it's going to converge. If that number is greater than 1, then it's going to diverge. It doesn't happen very often, and I don't want you to worry about that one too much, but just be aware that that does show up from time to time. Okay? Now, again, there's a lot going on here, but the next thing that I want to talk about is, okay, I know how to deal with 1 over x being raised to a power to tell whether or not it's convergent or divergent, but there are a lot of other functions that are more complicated than that. We can use, and this will come around again when we talk about what are called series, but we can use what is called as a comparison test. Basically, a comparison test is saying this: if I have a function like 1 over x squared that I know is convergent when I take the improper integral of that, any other function that I know for a fact that is going to be below that function the entire time will also be convergent. Now, that doesn't mean they're going to add up to the same thing, but I can use that information to figure that out. Like, for example, if I had 1 over x squared plus x plus 1, I might not know how to take the antiderivative of that. In fact, that would be pretty difficult to do. But if I were to look at the integral from 1 to infinity of 1 over x squared dx, I would know, because I'm adding things on the bottom here, I would know that this, because we found out already that this is a convergent integral, that this one would be as well. Now, they're not going to add up to the same thing necessarily, but I can say that I would know that those two will both be convergent. Now, obviously, there are a lot of other functions that work that you can't automatically tell whether it's going to be convergent or divergent necessarily right away. But it might take a similar form. Like, I've got 1 over e to the x squared. Now, we haven't talked about this a ton yet, but when I have an exponential function like I do on the bottom here, exponential functions grow much more quickly than polynomial functions do, which means this would be way underneath 1 over x squared. So I could compare these two, and I would know that this one over here is below this one. So although I might not be able to find out what it converges to, I would be able to tell that this is convergent because I know that the values of 1 over e to the x squared are always below the values of 1 over x squared. Sometimes integrals that have infinity have sine or cosine in them. Now, what you have to realize about a sine or cosine function, if I'm trying to tell whether or not it's convergent or divergent, is when I look at a sine graph, it goes up and down and up and down and up and down. The nice thing about that is the largest it's ever going to be is 1. The smallest it's ever going to be is -1. So if I think about this, if I put 1 over x squared, regardless of what it's actually going to add up to, again, I know that this is convergent, which means these values will always be larger than the values here, because if I put a decimal number on top, it's going to be smaller than 1, which is going to make it be smaller. So I could compare sine of x over x squared to 1 over x squared, and I would know that that is going to be a convergent integral as well. Now, you look at this one, what we have to realize in a lot of these problems is if I'm trying to tell whether it's convergent or divergent, I just need to look at the largest power of x. So this part is not going to matter because of the infinity portion. Well, if I've got the square root of x squared, that's the same as 1 over x. So if I did the integral of from 1 to infinity of 1 over x, it would behave very, very similarly to this function that we were talking about right here. So since this one is convergent, this too would be convergent because I could kind of compare the two and say, well, I know that one's convergent, so this one's going to be convergent as well. This is a hard idea to wrap your head around. Hopefully the examples we did to find out what they add up to made sense. And if you have any questions about this, please, please, please let me know.